Good morning, everyone. In the previous class, we are discussing something related to superconductivity and its technological applications. In the last class, we discussed what is superconducting phenomenon. So, what is the critical temperature and the invention or discovery of superconductivity, and also we discussed something related to the normal conductors and how the electrical resistivity occurs in normal conductors, and also we discussed some Matheson's rules, that is the variation of electrical resistivity as a function of temperature, and also the how the electrical resistivity increases within the material in the normal conducting materials. There are two important contributions. One is the resistivity due to phonon contribution. Another one is the resistivity due to impurity materials within the impurity atoms within the material. So now we understand how the electrical resistivity varies with respect to temperature. Now, the same thing, variation of electrical resistivity in superconductors as a function of temperature. But in the superconducting phenomenon is occurs only at very low temperature. So the superconducting phenomenon is not happened at happened at room temperature, even not more than 200 Kelvin. So it's happening. The superconducting phenomenon is very low temperature in the order of 5 Kelvin, 10 Kelvin, and less than. As of high temperature superconductor, it is around 146 to 150 Kelvin. Within this temperature range, the superconducting phenomenon is happening. So now as we know that the electrical resistivity of the material is suddenly dropped to zero at temperature of the system T is equal to Tc. This is we have already discussed. The resistivity is abruptly dropped to zero as rho tends to zero. What happened? The electrical resistivity. We know that the resistivity or electrical conductivity, which is equal to inversely proportional to rho. As rho tends to zero, then the conductivity tends to infinite. See, there are no resistivity within the material. The conductivity is infinite within the superconducting materials. I already mentioned this is an abstract idea. So we don't know the what exact the quantum mechanical behavior happening within the material. So this is the characteristic properties of superconductors. So now now we need to understand why these superconducting material shows zero resistivity. So before going to discuss that, we need to understand something related to important definitions. One is critical current, IC. We call it as a critical current. Then critical temperature, TC. Okay, and HC, critical magnetic field. Critical magnetic field. Field. So what is here high C, TC and HC? So what I'll do, in order to mention the brief description of these terms, if you consider a superconducting materials, I make it these aspect in a three-dimensional case, x, y, z. This is x, this is y, this is z. So I make it here. This is the temperature axis. That is, we call it as a TC. This is a critical current axis, or we can say um, magnetic. This is the HC. I'll consider, because the electric current and magnetic field are mutually perpendicular to each other. The critical magnetic field. So this is the critical current IC, and this is the critical temperature TC. See here, the superconducting behavior exists only within this region. Superconducting phenomenon. So within this region, you can observe here, this is the transition magnetic field HC. Below this, the material is superconductors. This is IC. Below this, material is superconductors. This is TC, the temperature less than critical temperature. These are superconducting nature, superconducting state. Also, we call it as a soft superconducting state here. Whatever the materials shows the superconducting behavior within this IC, TC, and HC, they are called as a soft superconductors. Also, we call it as a type 1 superconductors. Above this transition, for example, HC is greater than if you apply the magnetic field greater than the critical magnetic field, again the superconducting state is destroys, the material become normal conducting state. Conducting state. So here also, if you apply the magnetic field, the transverse magnetic field greater than the critical magnetic field, so superconducting state is going to be destroys. So therefore there is no critical current, there will be normal current. Of course, it is a normal current because of normal conducting state. Normal conducting state. And you increase the temperature of the system greater than the critical temperature. So again the material becomes normal conducting state. Normal conducting state. So within this region only the material behaves like a superconducting state. And the most of the pure superconductors, we can say generally, most of the pure superconducting materials, so for example, tin, beryllium, bismuth, and antimony. So these are the pure superconducting materials. So they shows the critical temperature less than 10 Kelvin. So if the superconducting materials having the less than critical temperature 10 Kelvin, they are all called as a soft superconductors. Soft superconductors. So if the critical temperature is less than 146 Kelvin, they are all high temperature superconductors, HTSC, high temperature superconductors. So what exactly here the critical current, critical temperature, critical magnetic field? These are the transition state. When within this region, the material behaves like a superconducting state. Above this, the material becomes normal conducting state. That is the second order phase transition. So now, this is about critical current, critical temperature, and critical magnetic field. Now, we need to understand the one more superconducting phenomenon is characterized by uh, Walter Meissner and Robert Ochsenfeld. So these are the two scientists. They shows one of the important characteristic properties of superconductors. That is, we call it as a Meissner effect. So it shows the superconducting materials are shows perfect diamagnetic in nature. Okay, so that is we call it as a Meissner effect. MEISS. Meissner effect. So what is Meissner effect? So this is also one of the important characteristic property. We can characterize the superconductors, one due to zero resistance, another one is zero resistance, another one is uh, diamagnetic nature, diamagnetic behavior. So we have discussed this, and we have only the abstract idea. We don't have deep insights of the quantum mechanical behavior of this thing. We will discuss later. Another one is the diamagnetic nature. Okay, so we will discuss the Meissner effect. In 1913, in 1933, Walter Meissner, Meissner and Robert Ochsenfeld demonstrated demonstrated the demonstrated an experiment demonstrated an experiment that is the expulsion of magnetic flux lines magnetic flux lines interior of the superconductor. Expulsion of magnetic flux lines interior of the superconductors is known as Meissner effect. MEI Meissner effect. See, we know that uh, there are materials which shows diamagnetic in nature in above room temperature also. But here we are talking the superconducting materials are shows perfect diamagnetic in nature. Why these superconducting materials are shows perfect diamagnetic nature? So that is the magnetic flux lines does not allows interior of the superconductor. The magnetic flux lines cannot pass through the superconducting materials. So means the superconducting materials repel the magnetic flux lines. It should not. It is not going to be allow the magnetic flux lines. So we will see the experimental demonstration with a brief description. For example, this is the normal conductor. Try to understand. This is the normal conductor. So generally what I do, for example, you can consider any copper or any material. So this is the normal conductor. You can apply the magnetic flux or the magnetic, you increase the magnetic field strength, the magnetic flux lines are pass through the material. So one thing is this is the temperature of the system is greater than the critical temperature. The temperature is not going to be critical temperature, it's greater than the critical temperature. So these magnetic flux lines are hollows the material. Magnetic flux lines are moving through this material. So B, you can take this is applied magnetic flux lines, so definitely it is some positive value. But whereas in superconductors, this is superconductors, okay, so these magnetic flux lines does not pass through these superconducting materials. So they're not. So these superconductors are expel the magnetic flux lines. So within this, what is the magnetic flux density within the material? Of course, it is zero because there are not magnetic flux lines not allowed. When the condition, the temperature of the system is equal to Tc or the temperature of the system less than critical temperature, only at this condition the material behaves like a superconductor. Above this, the material become normal conductor. This was a wonderful mechanism. The phenomenon was experimentally demonstrated by Walter Meissner and Robert Ogenfeld. So we call it as a Meissner effect. This is called it as a Meissner. After this Meissner effect, so this is the magnetic levitations. So we generally talk about what is the important application of this Meissner effect. So most of the uh, superconducting applications is based on this Meissner effect. For example, you can consider the magnetic levitated trains. So here there is no contact between the track and the wheel of train. So generally we say bullet trains. So that is the levitation. The magnet is levitating over the superconducting materials because of it's not allow the magnetic flux lines. So that is one of the important, wonderful experimental demonstration made by these two people. So this is an experimental idea, but we have to prove this by mathematically. So this is the experimental demonstration. We can also show that the superconducting materials are shows perfect diamagnetic in nature. So that is a proof of superconducting materials. Superconducting materials shows perfect diamagnetic in nature. We'll discuss that. So we know that from the magnetic properties of materials or magnetization of the system, we know that the magnetic materials, that is diamagnetic, paramagnetic, ferromagnetic, ferrimagnetic, antiferromagnetic materials, based on their susceptibility value, we categorize the magnetic materials. So here we are showing the superconducting materials are perfectly diamagnetic in nature. How do you uh, how do you prove this diamagnetic nature of superconductors? So we know that from the magnetic properties of materials, we know that the BA, which is equal to mu naught H plus M. So this is equation 1. So here this BA is the applied magnetic field, applied magnetic uh, flux. These are the magnetic flux. This mu naught is the permeability of free space. These are the magnetic flux lines is allowed by this thing, and H is the field strength, applied field strength, and M is the magnetization of the material. Right. So now uh, here this BA is going to be 0. Why? So because interior of the superconductor magnetic flux lines is 0, so that we put here BA is equal to 0, and mu naught H plus M. This is equation 2. But mu naught is not equal to 0, because mu naught has some value, that is 4 pi into 10 power minus 7 H per meter. But H plus M is equal to 0, then H is equal to minus M. Right? We know that susceptibility, that is magnetic susceptibility, this is the physical quantity which can determine the how much of material gets magnetized. So susceptibility, we can define the ratio of magnetization as a field strength. So we know that it is H is equal to minus M. You can substitute here the chi, which is equal to M by minus M. Mm gets cancelled, which is equal to minus 1. So the susceptibility chi is equal to minus 1. Of course. So based on the susceptibility value, we can categorize or classify the magnetic materials. If the susceptibility value is negative, those materials are diamagnetic in nature. If the susceptibility value is 0 or slightly positive or 1, it is paramagnetic material. And the susceptibility value is greater than that, there are ferromagnetic materials. So we proved here mathematically the susceptibility chi, which is equal to, for minus 1, this is diamagnetic. So we proved here the superconducting materials are perfectly diamagnetic in nature. See, this is also one of the important characteristic properties of superconductor. Still, this is an abstract idea. We don't know the uh, what is the quantum mechanics behind this theory. So how these materials behaves, or within the material, when you bring down to cooling temperature, how these materials are behave within the materials, what happened to the electron and the protons and lattice ions are interacting at very low temperature or cooling temperature. So still we do not know the brief quantum mechanical description of superconductors. Still, it's an abstract idea. So I already mentioned the superconductivity is characterized by one thing is zero resistance, resistance zero. Another one is it shows the perfect diamagnetic in nature. Perfect diamagnetic nature. These are the two important characteristic properties of a superconductors. Now, next we will discuss what is the quantum mechanical behavior of these superconductors. That is, uh, The in detailed, insightful information was provided by uh, three great physicists. One is John Burdeen, John Burdeen, another one Leon N. Cooper, N. Cooper, and Schreifer. Schreifer. So these two physicists or give a account of superconductivity, that is called as the BCS theory. BCS theory, or also we call it as the microscopic description of superconductors. Microscopic description of superconductors. Okay, we will understand this BCS theory, how this will be uh, explained. So we know that the John Burdeen he got Nobel Prize for second time for this theory. The first Nobel Prize for discovery of transition or invention of transistor. Uh, this is the second Nobel Prize he received. So we need to understand the super BCS theory or microscopic description of superconductors. Also we call it as a quantum mechanical description of superconductors. So BCS theory, we'll begin with the theory. In 1959, they proposed this theory. See, in general, we know that in the normal conductors, the electrons are flowing. They are constitute electric current. But in case of superconductor, what happened? Why this resistivity is going to be zero, and why these materials are shows perfect diamagnetism? These each and every details information we are getting in this theory. Okay, we will understand theory how it will work out. See, uh, again, the superconducting materials you are this BCS theory is meant only for BCS theory description is only applicable to applicable to soft superconductors, soft superconductors, or type 1 superconductors means the temperature less than 10 Kelvin, those materials, uh, the theory is applicable only for such materials. No, if the temperature of the system is temperature is around 50, 60, around 100 Kelvin, so this theory is not applicable for those materials. We will discuss that. As of now, for the high temperature superconductor, no precise theory was proposed by any other scientist. So only for BCS theory is the ultimate theory for microscopic description of superconductors. As of now, the till date, for the high temperature superconductors, no such theory is proposed as of now. If any person is proposed such theory, maybe he got the Nobel Prize. So now we will understand the BCS theory. See, again, you have to bring the materials to very cooling temperature, less than critical temperature. How here the electron behaves and lattice ions behaves. In the normal conductor, we know that as you increase the temperature of the system, the lattice ions is vibrating about their mean position. Is call it as a lattice vibrations or phonon vibrations. But if you bring down the material is very cool in temperature or low temperature, so how the mechanism is happen? So for example, this is a lattice ion. I call it as lattice ion, and one more lattice ion. So for the sake of representation, I took two lattice ions. This is lattice ion 1. This is lattice ion 2. Okay. So this is extended for three-dimensional case. You have Avogadro number of atoms, you will get Avogadro number of lattice ions and Avogadro number of electrons. So in superconductors, the temperature of the system, try to understand, the temperature of the system is less than critical temperature. It should not cross the critical temperature. So electrons is somewhere here in the region of solid, likely to be for this uh, lattice ion, and another electron is somewhere here. So this electron have negatively charged particle. This is a positive ion core. This is negatively charged particle, positive ion core. So this electrons, because of negative charge, it can slightly attracted by this positive ion core. See, so it is moving. It is coming over the positive ion core because of attractive force. So in between, there is a strong attractive force is created. Attractive force. And here also a strong attractive force. Okay, and electron somewhere he is here. Here also somewhere electron is here. So this electrons is also attracted by this positive ion core. This electron also was attracted by the same attractive force. Attractive force. Very important aspect here. See, according to the Coulomb repulsive force, we know that the Coulomb repulsion, if electron is here, another electron is very come closer to this electron, this is repulsion is happening. So the Coulomb force of repulsion. Coulomb force of repulsion. But this is happening in the normal conductors definitely, because the Coulomb force is unlike charges are attracted, like charges are repelled to each other. So now in the superconducting materials, you are bring down the temperature of the system is very low temperature. If the temperature of the system is very low, definitely there is no vibrations within the system. These lattice ions are not going to be vibrate because there are no phonon contribution. The temperature is cooling temperature. These are lattice ions. They are not vibrating about their new position. So this electrons is slightly attracted by this positive ion, and this electron is slightly attracted by this positive ion. Similarly, same thing here also. So now this electron have negative charge. So this electron cannot see this electrons. I mean, the C means this electron cannot feel the repulsive force of this electron. It's quite confusing, but when you bring down the temperature of the system, very cooling temperature for materials, the one of the wonderful or peculiar phenomenon is happening. That is, whatever this electron, they are fermions, they exhibit off integral spins. But when you bring down the temperature of these system, very cooling temperature, these electrons are behaves like a bosons. They are not become fermions, they behaves like a phonons. So here the spin is going to be zero, or according to the Bose-Einstein condensation or Bose-Einstein statistics or Bose-Einstein distribution functions, bosons are integral spins, that is 0, 1, 2, 3, so on. Whereas fermions, according to the Fermi-Dirac theory or Fermi-Dirac distribution functions, the fermions are half integral spins. But if you bring down the temperature of the system with very cooling temperature, so the fermions becomes bosons. Then these electrons cannot feel the repulsion of these electrons because they have integral spins, they have not off integral spins, and they cannot feel the repulsion because this attractive force is dominate this repulsive force. So if they are come closer and closer, this electron and this electron come towards ion core, this electron cannot feel the repulsion of this electron, because the property of the properties of these electron, like a fermions is becomes a bosons, because the cooling temperature, low temperature, these electrons are becomes a bosons. They have integral spins. So now here these repulsive force, this of course repulsive force is dominated by attractive force. So we can write attractive force is greater than repulsive force. So what happened usually? The wonderful mechanism. These two electrons, these two electrons are start pairing through virtual phonon. So this electron also start pairing through virtual phonons, and these the pair of electrons are gliding over a solid. They are without any disturbance, without any resistance, because there is no lattice ion vibration at all. So these pair of electrons are gliding or moving throughout the solid. So pictorially we can represent, so these are the lattice ions in the three-dimensional case. Write down like this, like this. These are the positive coins. So electron is here, they paired. So this is extended for three-dimensional case. These electrons are paired without causing any electrical resistance. They move throughout the solid, they gliding over the solid. So you can expect an infinite conductivity in superconductors, and provided it is only restricted for type 1 superconductor, this theory. So like this, they are paired each other, they move throughout the solid without any electrical resistance. This is the wonderful mechanism or the theory proposed by BCS, or Burdeen, Cooper and Schrieffer. So these pair of electron is called as a Cooper pair. Cooper pair of electrons. Cooper pair of electrons. So this is the microscopic description, and we have mentioned why the electrical. One thing is we characterized that why the electrical resistivity is zero, right? Resistivity is zero. But one more characteristic property, that is the perfect superconducting materials are perfectly diamagnetic in nature. How this? The same, the quantum mechanical description was mentioned in this BCS theory. So why these are going to be shows the perfect diamagnetic in nature. We'll see that. Same way now here we know that according to the Fermi-Dirac distribution functions, the electrons, protons, neutrons are off integral spins, and as per the Bose-Einstein condensation, this was the boson concept was explained by Satyendranath Bose. He was an Indian physicist. He worked with the Einstein, and he was the first person theoretically proposed the existence of bosons. After he worked with the Albert Einstein, uh, both are collaborated with each other, and they written a paper on bosons, that is Bose-Einstein condensation. So that is after this Bose is proposed about bosons. There are many Nobel Prize received in the field of superconductivity. But unfortunately, Satyendranath is not received. He is nominated for Nobel Prize, but he is not received the Nobel Prize. But after this, many physicists they got Nobel Prize. Till today date, many some people are received Nobel Prize. So now, one more important characteristic property, that is diamagnetic in nature, we have to um, explain in this PS theory. Already mentioned. See, if An electron, for the normal case, normal conducting case I'm explaining, if electron is spin, that is plus or minus half h cross. So how the magnetization occurs in the materials? We know that the magnetic moment, for example, you can take any paramagnetic materials or ferromagnetic materials. What is magnetization? Magnetization, the ability of the material get converted into magnetized, or the non-magnetic material gets magnetized, or the conversion of non-magnetization into magnetization. So that is known as the magnetization. That is, we call it as a representation M. How this magnetization occurs? Because of the magnetic moment or magnetic dipoles, that is mu m, which is equal to product of current and area. What is this current? Current is, of course, if electrons are revolving, if you apply the magnetic field, it is having spin. That is, spin is off h cross. Because of spin, you can apply the magnetic field. So this electrons takes a spinning. It's going to be spinning. Electron is spinning in a circular orbit. So because of the revolution, of course, there is a current. That is, we can say the current is charged per time period with an area. This is a electron is revolving. It's a circular. Area is pi r square. And this is magnetic moment, which is equal to E. T is the time period. That is E by 2 pi by omega into pi r square. So pi pi gets cancelled. So this is magnetic moment is equal to of E omega r square. This is the magnetic moment. So because of the magnetic moment, there will be a magnetization, because in the magnetic materials there are some domains. So in each domain, in the absence of, for example, you can consider this is the magnetic material. So you have a domains like this. So within this domain, the dipoles, that is the magnetic dipoles, are randomly oriented like this. When applied field strength is 0, in the absence of electric field, magnetic field, these are randomly oriented. Net magnetization of course is 0. Magnetization is 0. But when you apply the magnetic field, applied field strength is some positive value. What happened within this domain? So these are magnetic moments are aligned along the field direction. They are aligned along the field direction, and we can expect the net magnetization of the system. So this alignment is because of the spin of an electron. Spin is responsible for the magnetization of the system. So what happened in case of superconductors? They are perfectly diamagnetic in nature. I already mentioned, the electron is in the cooling at very low temperature or cooling temperature. The electrons are behaves like a phonons. Their spin, electrons are behaves like a bosons. The spin is going to be 0, 1, 2, so on. Integral spin. They have integral spin. Whereas the electrons are at room temperature or above that, they obey Fermi-Dirac distribution or Fermi-Dirac statistics. The spin is off integral, plus or minus off integral, h cross. So if you apply the magnetic field, if there are no spin, definitely there is no magnetization. These electrons are not attracted by the magnetic flux lines. One thing is, the spin is a very important role for the magnetization, but here these are bosons, so there is no magnetic flux lines allowed inside the superconductors. So here the electrons is pairing. It is having showing the integral spins, so the magnetization is 0. So If the magnetization is no zero, then the material is not at all diamagnetic, not at all magnetized. So then it is a diamagnetic materials. And here the electrons are also phonon and also lattice ions. They are also converted to phonons. They are phonons, or we call it as a bosons, because the phonons are also bosons. They have integral spins 1 2 3 so on. So how means, if you, for example, if you plot a variation of temperature with an energy, okay, so for example at higher temperature, so the materials becomes a normal conductors. So in each quantum state, there are not more than two electron according to Pauli exclusion principle. So here, as you bring down the temperature, is cooling temperature, you bring down this temperature to cooling temperature. So all these atoms, what they are excited in the higher energy state, they are come down to at very lower state and reaches a same quantum state. See, according to Pauli exclusion principle, this electron is plus of, this electron is minus of h cross plus h cross. So same thing in each energy state. So not more than two electron is existed. But if you bring down this temperature to very cooling temperature, so the all these uh, particles are come and occupy the same quantum state. See, these electrons is occupied in the same quantum state means, so spin is not come to picture here, because these atoms are converted into bosons, because the temperature of the system is very cooling temperature. So this is the Bose-Einstein condensation. Einstein condensation. The same mechanism is happened in the superconducting materials. That's why the superconducting materials are shows perfect diamagnetic in nature. So this is a wonderful quantum mechanical description of superconductors. And not only the BCS theory explained this, the proof of zero resistivity and perfect diamagnetism, and also the BCS theory shows that the superconductors have energy gaps. That is energy gap in superconductors. And also the BCS theory shows the isotopic mass. So these are the further studies made in superconducting, microscopic description of superconductors. There are many mathematical formulations to framework this BCS theory. Uh, in order to understand the in detailed or insightful information uh, of superconductors, again we need to learn more about BCS theory. Then we will get to know so what are the specific heat of superconductors, and the energy gap in superconductors, and isotopic mass in superconductors in this microscopic description. So this is about brief quantum mechanical behavior of superconductors. Um, in the next class, we will discuss the type 1 and type 2 superconductors and its importance in technological applications. Today I will stop here. We will continue in the next class. Thank you.